So if you're a Java developer, you have definitely been here. You need to store a bunch of items, you need to keep them in a specific order, and yeah, duplicates are totally fine. So you reach for the list interface, and then you hit that classic crossroads. ArrayList or LinkedList. I mean, on the surface, they look almost the same. But as we're about to find out, it's what's happening under the hood that changes everything. Let's dive in. I mean, just look at these two lines of code. They're pretty much identical, right? The only thing that's different is that one little word. So it's easy to think, does it really matter which one I pick? And the answer is, oh, you better believe it does. And that's really the big question we're tackling here. What is the fundamental difference hiding behind that super similar code? Well, the answer goes deep into how they actually store your data, and it has a massive impact on your application's performance. So to figure this all out, we've got to pop the hood and see how the engine works. First up to the plate is the one most developers grab by default, the array list. You know, at its heart, an array list is pretty much exactly what it sounds like. It's a list that's backed by an array. And this is the key detail. It means all of its elements are stored right next to each other, side by side, in one continuous block of memory. Sure, it's dynamic, it can grow and shrink, but that underlying array structure, that's the secret to everything it does. So picture this, an array list is like a train. Each piece of data is a car, and they're all linked together in a perfect numbered sequence. If I tell you to go find car number 5, you don't have to start at the engine and count your way back. You know exactly where to go. That's what we call random access. And here's why that matters. Because of that train-like structure, grabbing an element by its index, its position, is incredibly fast. In computer science, we call this O of 1, or constant time. It means it takes the same tiny amount of time whether the train has 10 cars or 10 million. But what if you need to remove a car from the middle? Well, now you've got a problem. You have to shift every single car behind it forward to close the gap. That is slow. It's an O of n operation, because the amount of work you have to do grows with n, the number of elements in your list. All right, so that's the array list built for speed when you need to grab stuff. Now, let's flip the script and look at its counterpart, which is built on a completely different philosophy, the linked list. A linked list basically throws that idea of a continuous block of memory and just throws it out the window. Instead, every single element is its own little object called a node. Now, each node holds your data, but it also holds two very important pieces of information: a pointer to the next node in the list and a pointer to the previous one. So if the array list was our train, the linked list, it's a scavenger hunt. Each item is like a clue that only tells you where to find the next clue. If you want to find the 5th item, you have no choice. You have to start at the very first clue, which points you to the 2nd, which points to the 3rd, and so on until you finally get there. You have to walk the chain.
And the scavenger hunt structure completely flips the performance on its head. Now, adding or removing an element from the middle is super fast. It's O of 1, constant time. Because all you have to do is find the spot and just rewire a couple pointers. Easy. But trying to get an element at a specific index, that's our scavenger hunt. It's a slow O of n operation, because in the worst case, you might have to walk through the entire list from the very beginning.
So what we have here are two very different ways of doing the same job, each with opposite strengths and weaknesses. It is time for the performance showdown. Let's just lay it all out side by side. For data storage, ArrayList uses that contiguous array, while LinkedList uses those linked nodes. This gives ArrayList blazing fast O of 1 access time, but makes its insertions and deletions in the middle slow at O of n. LinkedList is the exact opposite. It is fast O of 1 insertions and deletions, but that access time is slow at O of n. And one more thing to remember, memory. LinkedList has more overhead because every single node has to store those extra pointers. Okay, the theory is great, but what does this actually mean for the code you write every day? The real power here comes from knowing when to use each one. So let's talk about choosing the right tool for the job. You know, the classic advice here is actually pretty straightforward. If your program is mostly just reading data, grabbing items by their position over and over again, ArrayList is your champion all day long. But if you're constantly adding and removing elements, especially from the middle of the list, then LinkedList is the clear winner. But hang on a second. What if I told you that this choice between ArrayList and LinkedList affects more than just the speed of your code? There's actually a pretty surprising modern twist to this whole debate. 300%. What on earth could that number possibly have to do with choosing a list? Believe it or not, recent studies have shown that making the wrong choice here can jack up your application's energy consumption by as much as 300%. In a world of battery-powered phones and giant data centers, performance isn't just about speed anymore, it's also about being efficient with power. Now, that 300% number is, well, it's pretty dramatic. But before you run off and start refactoring all your code, we have to remember a critical piece of wisdom from computer science legend Donald Knuth. He famously said, "Premature optimization is the root of all evil." And Knuth's point was this: for the vast majority of your code, what he estimated as about 97% of the time, making sure your code is clear, readable, and correct is way more important than these tiny little optimizations. These performance differences are real for sure, but you should only really worry about them in those critical, high-traffic parts of your application where you've actually proven there's a bottleneck. So if we shouldn't always be chasing these micro-optimizations, then what is the single most important takeaway here? What's the best practice for writing code that's strong, flexible, and easy to maintain down the road? And here it is. This might be the single most important professional habit you can build. Code to the interface. Look at this line again. Notice how we declare the variable using the interface, list, not the specific class, ArrayList. This one simple habit gives you an incredible amount of power. It means if you do find a bottleneck later, you can switch from an array list to a linked list by changing one single word. The rest of your code doesn't care. It just knows it's talking to a list. And there you have it. Two powerful tools, two different philosophies, each with a clear set of pros and cons. It's a classic engineering trade-off. But now you have the knowledge to make that choice and make it wisely. So the only question left is, what are you going to build?